All right, so today we're talking about transformers. So we learned about attention last time, and we're going to take that to the next level with transformers, where we will introduce self-attention. Start off, just a bit of business. Lab 6 is due this Saturday. That's the char RNN lab. Any questions on Lab 6? Get in. Yeah, so you're wondering, so we're predicting, well, so you have your HT for each step of your RNN, right? So you should have a linear layer after that HT to try to predict which token comes next. And so that linear layer will not be part of your GRU. That will be, we'll call that a prediction head, which will go from the HT dimension to the dimension of your vocabulary, predicting the next token. Does that answer your question? Okay. All right. And then, yeah, from there you can use beam search, or you can use sampling, or just greedy decoding, any of those algorithms we talked about in class. Okay. Anything else on Lab 6? All right, and then, as usual, we have readings due this Saturday. Okay. Last time we talked about attention, neural machine translation. We took a look at that bidirectional attention RNN that Google used for neural machine translation. And then we went into talking about embeddings and how we can learn these representations of words. So just a quiz to try to refresh your memories. So this is the question. In the skip-gram negative sampling algorithm, what would happen if you didn't have negative sampling? If you removed that part of the objective? And you can go ahead and discuss that with the person next to you. All right, what do you think? Let's actually try to get a show of hands. Who thinks the answer is A? Raise your hand. Got a couple. Who thinks the answer is B? A lot more. Who thinks the answer is C? A couple. All right. So let's hear from some of the people who thought it would be C. Why did you think it would be C? Okay, it's all right. Yeah, so the correct answer is B. Does anyone feel like they have a good answer for why all the word embeddings would be learned to be the same? Yeah, Grant. Exactly, yeah. So if we remember, our skip-gram negative sampling algorithm had two objectives. One, maximize the similarity between our word embedding and the context. And the other was to minimize the similarity between the word embedding and a randomly sampled context. And so, like Grant said, if we didn't have the negative part of that, we could just learn to map all of the embeddings to the same part of the space, and we would maximize the objective. So we have to have some sort of negative objective to spread the vectors out so that they only are similar to contexts that they're similar to. Good. What would happen? What do you all think would happen? This isn't this quiz question, but what do you think would happen if we left out the positive sampling and only had negative sampling? Yeah, what do you think? Yeah, exactly. Yeah, so the word mesh, I don't know if they would be perfectly orthogonal to each other, but yeah, the word embeddings would basically all be pushed apart from each other. So um I was wondering if that was maybe what the people who picked C were thinking along the lines of. But yeah, so those are kind of the two aspects of the word embed of the skip-gram negative sampling algorithm. So today we're going to take a look at the transformer, and it's kind of intimidating to look at in math, but hopefully we'll break it down simply enough that you can kind of understand the intuition of where the motivation for this architecture came from. So a couple big ideas for the transformer. So first of all, we don't like recurrence. Number one, because we have those long context windows that we have to deal with, and basically memorizing information into a single vector. Number two, if you've noticed training your recurrent neural networks, you have to sample one token before you can get the next. And so that's kind of a slow operation. So yeah, during training for recurrent neural networks, you have to basically unroll sequentially in order to predict an entire sentence. Whereas with the transformer, you can predict an entire sentence during training in a single step. Yeah, and so basically the idea in transformers is that we will use a self-attention mechanism at each step and drop out all recurrence. So for example, let's take the sentence, I went fishing on the bank. Okay, so bank is a word that can have multiple meanings, right? That depend on the context. It could be a bank with money, or it could be a riverbank. And so in order to know, for a person or a language model to know which bank we're talking about, you need information from the context. And so to do that, what the transformer will do, and we kind of saw examples of this with attention already, is we will compare the word bank to every other word in the sentence. And the result of those comparisons gives us an attention score, which we will use as a weighted combination of all of the other words to create a new updated embedding for the word bank. Now that might start to sound kind of familiar from our last lecture. It might kind of start to sound like the skip-gram word embeddings that we were talking about, right? Because the whole point of those was to basically make words similar to their context. So this is a similar idea where we are basically saying that our embedding of the word bank is based on a weighted combination of the words that surround it. Only the difference here is that with word embeddings, we were just learning one universal embedding for the word bank, whereas in the transformer, every different sentence that the word bank appears in, it will have a different embedding as a different weighted combination of its context. So for example, think about what would happen if you tried to train an embedding for the word, let's actually use a different one. Let's say Macintosh. A Macintosh could, or a Mac, or let's do Mac, because Mac could refer to macaroni and cheese. It could refer to your laptop, or it could, well, yeah, we'll just say mac and cheese or your laptop. Okay. What would happen if you tried to train a word embedding for the word Mac? What do you think? Which word embedding would it pick between the two? Yeah, what do you think? Yeah. Yeah, so it might go to the one that's more frequently used, or it might end up being like somewhere in the middle in some random part of the space that's like half macaroni and cheese, half laptops, which you can imagine isn't very useful. So there's a huge benefit to being able to learn context-dependent embeddings that are different for each context that a word appears in. And that's what transformers do. So here's just a little visual of what happens during one layer of attention. So we have 4 words, and they all pass information between each other and create updated representations of all of those words in context. And you do so again. And then, so this is using a transformer for translation. So you have this encoder part where you're learning new embeddings for each of all these words, contextual embeddings for each of these words. And then you use these contextual embeddings as well as the previous context of the predicted words to predict the new words. Did that go too fast? Do we want to see that again? Okay, let's look at that again. We'll start about halfway through. So are we good up to here where we have these contextualized embeddings of each of our words? Yeah, Joseph. What was that? Yeah, so these dots in the middle would be the output of our encoder. And so you might be noticing something here. Normally our RNN spits out only, compared to an RNN, we only get one embedding for the entire sentence. In this case, we're getting an embedding for each word. So this is very similar to an attention RNN, right? Because in an attention RNN, we store representations for each of the words. Yeah. Correct. Yeah, so yeah, so the initial embeddings are uncontextual, right? They're just the words. And then in between the first 2 rows of dots, we have one transformer layer. And then between the next 2 rows of dots, we have another transformer layer. Exactly. It's like context upon context upon context, which is really where the power of self-attention comes in. Because, well, yeah, we'll leave that discussion for a little later in class. So we have embeddings for each of our words. Oops. Okay, we're just starting over. So I want you to look at where we take information to predict our first token. So here we get information from the start token and all of these other tokens to predict J. Then to predict Suisse, we take info from start and all of these other tokens, and as well as J to predict Suisse, and etc. So we basically have attention between everything. Yeah. First, it just embeds within a sentence. So that would be the encoder part. Yeah, and then it takes information, and then it also embeds the words that it is decoding. And so, and then all of those embeddings are used to predict the next token. Okay, yeah, Jared. Great question. Yes, it absolutely does. So you've observed something very important, that we've taken out recurrence. So where does the ordering come in? And the answer is we're going to use a trick called a positional encoding, which will be basically something that we add to each of these embeddings that represents its position in the sequence. So yeah, and we'll get to that later, but that's a great observation. So to kind of further motivate this idea of attention, here is an example of a problem called co-reference resolution, where you are trying to figure out which nouns and pronouns in a sentence refer to the same thing. So in this first sentence, what do you think the word it refers to? Probably the animal, right? And how did you determine that it referred to the animal? Because animals are what get tired. Exactly. So yeah, we have two nouns in this sentence, animal and street, but you decided in this case that it referred to animal because you saw the word tired. Now, how about here? What do you think it refers to? Probably the street. Why? Because wide usually describes streets more often than it describes animals. Exactly. And so in order to do that, you can kind of see the hops of attention that you did in order to determine which noun the word it referred to. And you can see that an attention-based neural network learns the same things. So we are updating our embedding for the word it, and look where it looks in the first sentence compared to the second sentence. In the first sentence, and the weight of these lines, the darkness of these lines, and the darkness of these boxes correspond to those attention values that we use as weights for when we take a weighted combination of the inputs to update our embedding. So we can see that there's a higher weight on animal to update it in the first sentence, and there's a higher weight on street to update it in the second sentence. Yeah, Brendan. Yeah, exactly. So somehow we needed to have a way of figuring out, yeah, how did the network learn to weight animal high in this setting and street high in this setting? I'm guessing it's because in a previous step, we took information from the word tired to update the word it, or to update probably took information from the word tired in this first sentence and took information from the word wide in the second sentence. So this is the overall architecture. So it is encoder decoder, and we can do tasks that are many to many. So, well, actually, we can do all types of tasks. So many to one, one to many, many to many. And those many to many can have a different number of tokens in each. In this case, we have 3 tokens in the first input and 4 tokens in the output. So let's blow this up a second. And also credit goes to the Jay Olimar blog for these awesome visualizations. Yeah, these are basically copied and pasted from that. So yeah, inside this transformer, we have an encoder and a decoder. And if we want to blow that up even further, within this encoder, we have n encoder layers. We will call these self-attention layers, and n decoder layers. And the way it works is we encode this input sentence and then take the output of the last encoding layer and feed that into each of the decoding layers. If we want to blow that up even further, we have what do these encoder and decoder layers look like? Well, we have what we will call a self-attention block, followed by a feed-forward network in the encoder layers. Does everyone know what a feed-forward network is? No. Yeah, so a feed-forward network is just a linear layer. It's kind of annoying how some terms are overloaded, but yeah, that's just a linear layer. WX plus B. Yep, multiplying by a matrix and adding a bias, WX plus B. Yep. Okay, then in the decoder, it's a little bit different. So if you remembered, we had an arrow going from the encoder to each of the decoders. And so we have to have some way for the decoder to look at both the decoder input as well as the encoder input. And so that will be combined in the encoder decoder attention. And then there will also be self-attention on the decoder inputs. And we'll get to what those are in a second. And actually, I will just tell you. So in this case, when we're doing translation, the decoder inputs would be exactly the same as the decoder outputs. So this is kind of tricky. So the question is how do we predict these if we're providing them as inputs? And the answer is that we perform masking so that each token in the decoder output can only see the tokens that come before it and cannot see itself. So basically and so this is a little bit different from the attention RNN we saw. In the attention RNN, the decoder could only look at the encoder input, but with the transformer, we want to be able to also look at the previous tokens in the decoder. So we want to be able to see Je suis étudiant and I am a when we are predicting the word student. And so that's what providing I am a student as input to the decoder allows you to do. Does that kind of make sense? Yeah. Yeah, so when predicting the very first token, you would only have encoder output, exactly. And so you would have a start token. So the inputs are the outputs shifted right. So you'll have a start token, I am a, would be the inputs to the decoder. Yeah.
So the encoder.
Exactly. Yeah. So the decoder self-attention, this first block, only has access to the previous tokens in the decoder, but then those are combined with the tokens from the encoder in the encoder-decoder attention. So in total, the decoder can see all of the previous tokens in the decoder, as well as all of the tokens in the encoder. Yeah, so translation. Great question. Yeah, that is a great question. So what if you're doing many to one? And the short answer is that you actually don't have to have both an encoder and a decoder. So this is kind of the encoder decoder is a general case, but we can simplify it. So most many to one tasks only use an encoder. Exactly. Yeah. Yeah. Yeah, question. Good question. So the question is whether each encoder block takes input from all of the previous encoder blocks or just the one that immediately came before it. And the answer is technically only information from the one before it, but there are skip connections in here. And so it can effectively take information from all of them. And those skip connections just come in the form of adding the output of the previous layer to the end of your current layer. All right. So yeah, we talked about context-sensitive representations, and now we are going to take a look at a blog post. I'm up on the video. Good. Okay. So full disclosure, I wrote this blog post, but I think it's pretty helpful. So hopefully this helps. Can you see like what this says? That's probably pretty small in the back, huh? Okay, let's see. Can make this any bigger. Is that any better? How big we can go without losing stuff. Okay, so this is none of this on here is a transformer. This should all look familiar. So we have an RNN on the left and an attention-based RNN on the right. And so to show you where we're going, what we're looking at is we're looking at the relationships between RNNs, attention-based RNNs, and self-attention to kind of show you where these ideas came from. So I want you to take a look at this vanilla RNN and this attention RNN next to each other. And the reason why I kind of wrote my own blog post on this is because I wanted to basically simplify these to show the similarities between them. So we've taken out a lot of details to show basically on the most fundamental level how RNNs, attention RNNs, and self-attention are related to each other. So looking at this, what do you see as being the differences between a vanilla RNN and an attention RNN? And also, if you can't see in the back, you can pull up this blog post on Learning Suite as one of your readings for the week. Yeah. All right. What do you see as far as similarities and differences? Yeah. Right. Yeah. There's no connection, no direct connection between previous layers H1 and the current layer HL-1. Yeah. Good. Let's see if we can understand what's happening here in the top of the attention RNN. So, yeah, first of all, here we have lines going from each of our H's into a matrix that is D by L-2. So this matrix on the left is just storing our hidden layers at each step. Yeah, question. Full screen it. So unfortunately, these are two different windows. So if I full screen, we'll only see one of them. Try to go a little bigger. Although I don't know if that's actually making the diagram any bigger. I'm sorry. Yeah, but if you can't see it, like, and you have a laptop on you, I definitely encourage just like pulling it up so we can be looking at the same thing. Yeah, so first step is we're going to gather all of our previous hidden states into a matrix. And then here in the bottom right, we're taking basically that exact same matrix except transposed, and we're going to compute the dot product between the current hidden state and each of those hidden states, each of those previous hidden states, to come up with attention weights. And so that can be, you can think of that as a matrix multiplication, taking us from L-2 by D hidden states by a D by 1 hidden state into L-2 attention weights. Any question on how we got those attention weights? Yeah. Exactly, yeah. Exactly, yeah. Yep, so each of these attention weights represents a similarity or compatibility of our current hidden state with each, respectively, each of the previous hidden states. Did you have a question? L is the number of tokens. Yeah. Hey, Jaden.
String. Vanilla. Row. Got to. Oh.
Yeah.
Like
Yeah, I mean, you could definitely see it that way. I think the argument for attention is that we see that attention is better. Do you remember that graph that we saw where as the sequence length increased, the accuracy of the LSTM tapered off, whereas the attention, the performance of the attention RNN stayed flat? That's really our motivation. It's showing, LSTMs try to do this like memory gating thing where they try to squeeze all of that information into one vector, but they just aren't able to. There's inevitably information loss. And then the other real benefit is that we can make a custom context vector for each new token to predict. So we can take a different weighted combination of our previous hidden states based on the current token that we need to predict. Whereas we just had one context vector to deal with for all of our hidden states in an LSTM. Yeah. Okay. So any more questions on how we got our attention vector, or just general question? Okay. And then we take a dot product between our attention vector or matrix vector multiplication between our collected hidden states and that attention vector to give us a final context vector, which we will use to predict the next token. So are we good on how how the RNN relates to the attention RNN? Yeah, Jaron. That is a really good question. Yeah, you could totally think of it that way. Yeah, and that's actually kind of a reason why. Well, yeah, actually, we're just not going to go into that. But that is a very insightful observation. So now we're going to compare the attention RNN to a self-attention RNN or a self-attention network. Okay, so yeah. We have been, yeah. In the attention RNN, we computed context vectors for each one of them. Yep. Aren't they just a linear layer applied to the? Good question. So actually, I'm not 100% I understand your question. So at each step, we produce a context vector based. So let's take machine translation. So let's do Spanish because I've had enough butchering of French and I know Spanish. So I am a student. Yo soy un estudiante. So we first get hidden states for I am a student, and we have those collected in 4 hidden states. I am a student, and then we have the start token, and so this is at training time. We'll take the start token, get a hidden layer representing the embedding of the start token, and do the dot product of that hidden layer with each of the with I am a student, and yeah, attention weights, create a weighted combination of those, and then that becomes our context vector for predicting the word yo. And then we pass that context vector through a hidden layer and get a prediction for that, for the word yo. And then we do the same thing for the word soy. We'll take as input the word yo, or start token and yo, and we would get, we would just get a hidden state for the word yo and do the dot product of that with all of the previous hidden states. And that would give us attention weights, which we use to create a weighted combination of I am a student, which gives us a new context vector, which we use to predict the word soy. Does that answer your question about how we use it previously? Okay, I think, yeah, go ahead, Joseph. So these diagrams are for inference. Yeah. Correct. Yeah. Yeah, I think we may move on from your question, and hopefully we will answer in the rest of the class. If not, you can come and talk to me in office hours and we can spend some more time with it. Yeah, so we're going to move on to self-attention and try to see how it relates to a normal attention RNN. So you should see a lot of similar building blocks on the left side as you do on the right side, but also some things that are added and some things that are left out. What are some things that you notice that are added and left out in the self-attention compared to normal attention? Yeah, what do you see? You said an additional encoding and word. What was that? Yes, yes, positional encoding and word embedding. Yes, so that's what we see right here. Yeah, so we no longer have, you'll notice that we no longer have these arrows. So we've gotten rid of recurrence and replaced that with a positional embedding. And so this is, you can probably think of several ways that you might implement a positional embedding. But we'll go over the details of that later. And so we have a positional embedding concatenated to a word embedding. Okay. Yeah, what else do you see that's different? Yeah, Brendan. Yeah. Mm-hmm. Yeah, exactly. So Brendan noticed a couple of things. First of all, instead of just taking direct copies of our hidden states, we're going to pass them through a different linear layer for each different function that those hidden states are performing. So we'll have one linear layer for basically our memory of the hidden states. We'll have a different linear layer for computing our attention matrix, and a third different linear layer that we're using to transform what we will call our query, which corresponds to the current hidden state. Yeah, what else do you notice that's different? There's one major difference. Yeah, what do you see? Yes. Yes, exactly. At the top of the self-attention network, we have many context vectors instead of just one. Why is that? And I'll tell you that the answer has to do with by following the arrows. If you follow the arrows, you can figure out why we have more, and also the dimensions of these matrices. You can figure out how we get more context vectors and what those correspond to. Yeah. Good question. It does not have to do with the order of the words. Exactly. Yeah. So I'm sorry, remind me your name. Chase. Yeah. Chase noticed that we're predicting more than just one character. We're predicting X2 to XL. And so this is a huge advantage of attention-based networks over recurrent. For recurrent, we had to basically do a pass through our neural network for each new token that we wanted to predict. With attention, we can simultaneously predict all of the subsequent tokens, get a loss on all of them, and back propagate. And the way that we do that, if we want to trace this, so the difference is we have a V by 1 output here in the attention RNN, and a V by L-1 output in the self-attention network. Where does that L-1 come from? Well, we had L-1 context vectors. And that came from the fact that we, instead of having an L-2 by 1 attention vector, we had an L-1 by L-1 attention vector. That came from the fact that we had L-1, basically, we will call these query vectors, we'll call these query vectors. And yeah, that came from the fact that instead of just comparing our last hidden state to all of the other hidden states, we compared all of our hidden states to all of the previous hidden states. So instead of just doing attention between the last hidden state and all of the others, we're doing full, what we will call self-attention, where all of the hidden states get updated based on all of the other hidden states. Here's a question for you. How many attention layers can you stack on top of each other? The answer is you can only do one because you're taking a sequence of length L-1 and producing a context vector of length 1. How many self-attention layers can you stack on top of each other? As many as you want, because we can then take these L-1 context vectors and then pass them into a further transformer layer, which does basically context upon context, and then another layer which does context upon context and upon context. And we basically build these extremely rich representations of each of our input tokens that comes on combining, basically taking contextual information over and over and over. So if you remember the Google neural machine translation, it had many LSTM layers, but only one attention layer. Transformers, we can have as many self-attention layers as we want. So that's kind of like one of the huge benefits of transformers as compared to just attention-based RNNs.